Hi everyone, this is Mrs. J. Today we're going to be finding volumes of rotated solids using shells. Alright, I have a quick warm up for you guys, so please pause the video and give it a try. Alright, go ahead and check your work here. So here you can see I have my original bounded area, and then first we're rotating about the x-axis. So remember, when you have a horizontal axis, your washers are going to be vertical. So if I'm stacking my washers vertically, I'm actually going to be kind of sliding them left to right. They're going to stack horizontally next to each other. So when I have something like this, maybe we could draw in a little arrow from here to here. And that means I'm integrating with respect to x, because again, they're stacking up horizontally. And then you can see here's my large radius, and then this distance is my small radius. And then we have pi r squared minus pi r squared. So it's large radius minus small radius. And then again, it's from 2 to 5. Now when I'm rotating around the y-axis, now I have horizontal washers like this. So these I'm going to stack on top of each other. They're going to stack up vertically. So I'm integrating with respect to y. So that tells me that I need to make sure my equations are all with respect to y. And it also tells me that I'm going to integrate from 1 to 2. So you can see my large radius is this distance, and my small radius is from my parabola to my y-axis. And then we're going to integrate. Alright, so today we're going to learn an alternative to the disc or washer method, which is called the shell method. So for some problems, you can kind of use either method interchangeably, but there's definitely some problems where the shell method will be much easier to work with. And likewise, there's some problems where the disc or washer method will be the easier one to work with. So this method is pretty different from the washer method. The first main difference is that now when we take our little cross section, our slices are going to be parallel to our axis of rotation, which is different than when we were doing the disc or washer method. So imagine here's a rotated solid that's actually cut in half except for this middle part. And then you can see that this solid has been rotated about the y-axis. So here, if you take vertical cross sections, super thin little vertical cross sections, and then you kind of unwrapped it, you were kind of peeling off this layer going all the way around. You could see that you have these little cylinders. They're kind of these cylinders that wrap around. And again, I know that this one, it looks like it's kind of a big jump. This doesn't look like it'd make a smooth curve when our slices are this thick. But imagine they were infinitely small and you stack them next to each other. It can still generate a very smooth looking curve. I think you can see that a little better here. There's more of these peels. So again, we're slicing parallel to our axis of rotation, and we're taking that slice and we're kind of peeling it off our curve. Now, when we do that, when we peel that slice off our curve, so imagine we took this cylinder, right? We peeled it off and then we opened it up. When we open up our peel, it's actually just a rectangle. So imagine I'm opening up this slice, and the height of my rectangle is going to be dictated by the height of my solid at any point over my interval. And then this width, the width of my rectangle, is dictated right here, 2 pi r, which would be the circumference of our solid at that point. So the idea for this method is we find a way to define the area of any arbitrary peel, and we can do that by 2 pi r h. And then we can integrate over our interval, so we can take into account all of the different peels that are infinitely thin, infinitely small within that interval. Now here I just have a quick comparison of our two methods. So I want to focus in on how we slice, so how we find our cross section, and I also want to talk about how we integrate with respect to what variable. So for these two problems, we have the same bounded area. Here it's a y-axis rotation. So if we were using that disc or washer method, remember we always slice perpendicular to our axis of rotation. So our slices, in this case, are horizontal, and I need to stack them on top of each other. So they're stacking like this, which is why I'm integrating with respect to y. Now, today we're going to be working with the shell method. So since I have a vertical axis of rotation, I'm going to have a vertical cross section. And if you have a vertical cross section, well, we have to slide them side to side to stack them. So that's how we're going to integrate. So here we'd integrate with respect to x. So determining that is going to be a really big part of today's lesson, so we know how to set up our integral properly. And then if you look at same scenario, but now we have an x-axis rotation. Again, since it's horizontal, if we were using disk method, our disk would be vertical, and we have to stack them side to side, so we integrate with respect to x. And if we're using shell method, we'll have a parallel cross section, so also horizontal. And these I must stack vertically, so I'm going to integrate with respect to y. And then, of course, the other big change is for the disk or washer method, you're actually adding up areas of circles or washers. So you use pi r squared. But today with the shell method, we're adding up areas of rectangles. So that's why we have the 2 pi r h. Again, two different areas that we're working with. And it just depends on how you slice your cross section. If you slice perpendicular to your axis of rotation, it will create a disk or washer. And if you slice parallel to your axis of rotation, it will always create that cylinder, which we unwrap into a rectangle. All right, let's give one of these a try together. So here, let's start by sketching out our bounded region. So we have this quadratic function. So if you factor it, we can figure out where our zeros are. So we have a 0 at 0 and 6. And so we know that our vertex must be at exactly somewhere on the line at x equals 3. So if you plug in 3, we get that the vertex is at 3, 9. So here's our quadratic. And then it's also bounded by y equals 0. So I'm going to stop at the x-axis. And there you have it. So this is our bounded area. And here we're going to rotate this one about the y-axis. So I'm going to draw out the rotation for this problem. But maybe I'm not going to do that for every single problem. But it would end up looking something kind of like this. Here we go. Okay, so remember the first thing we need to start with is deciding on how to slice our cross section. So since I have a vertical axis of rotation, I'm going to have a vertical cross section like this. And that cross section is always going to be the height of our rectangle. So it looks like this. Now you can see from the get-go, since I have this vertical cross section, the only way to stack them up would be side to side like this. So here I'm going to be integrating with respect to x. So that's good because our equation is already with respect to x, so I don't need to rewrite my equation. Now, if you kind of turn this cross section into that cylinder, so again, if you looked at it as a peel and you wrapped it all the way around your rotated solid, it would make this type of shape. So it's a cylinder. And then the idea is that we're going to unwrap that cylinder into a nice rectangle. And then we just find a way to define the general area of any of those rectangles. So this is h, and remember this is 2 pi r. So you can see we need to define two things. We need to define h in terms of x, and we need to define r in terms of x, because that's how we're integrating. And I can see r is just going to be this distance. So I like to actually write these out on the side. I can see that h is going to be the distance from my quadratic to the x-axis. So it's always top minus bottom. So in this case, h is 6x minus x squared minus 0. And remember, I need to define my radius in terms of x. And I can see since I'm starting right at the origin and I'm just moving to the right, my radius is just x. r equals x. And again, x, it's arbitrary. It can be any x value over this interval. And then depending on the x value, that will dictate the height of any individual rectangle. So I can define the area of our individual rectangles by saying 2 pi r, which is x, times the height, 6x minus x squared. So again, this is the area, the general area of any rectangle within my solid. So now I need to set up my integral. So I'm going to integrate, I can see from here to here, so from 0 to 6, and I'm just integrating this area. So I'm always going to pull the constant, the 2 pi out front, and then all I have left is the x times 6x minus x squared, so 6x squared minus x cubed dx. And that is my integral. Now from here, this is all stuff that we did last chapter. It's simply evaluating our integral. So we'll find that antiderivative. So 2x cubed minus 1/4 x to the 4th from 0 to 6. So we have 2 pi times 2 times 6 cubed minus 1/4 times 6 to the 4th. And for this one, we end up with 216 pi, and then all of these should be units cubed. So for today, I really want us to focus on the setup of our integral. So understanding, how to create our cross section. Our cross section is always going to be that height of our rectangle. Understanding which variable we're integrating with respect to, and then understanding how to define h and r in terms of that variable. All right, let's try another one together. So we have a bounded region by 2 minus x squared, y equals x, and x equals 0 in quadrant 1. So I'm just going to stick in quadrant 1. Here's the start of my 2 minus x squared. So I know it's going to go down like this, but then I also see I have that y equals x like this, and here's x equals 0. And again, it's in quadrant 1. And this one we are also rotating about the x or the y-axis to form a solid. So for this one, the rotation would look kind of like this. There you go. So it actually kind of looks like an ice cream cone when you rotate it around. Now, for this one, same idea as the last one. I have that vertical axis of rotation. So I have a vertical cross section, which is the height of my rectangle. So this is h. And since I have that vertical cross section, I can see that I'm sliding it from left to right to cover the entire area of that bounded region. So since I'm sliding it from left to right, I'm integrating with respect to x, and then it's going to be from 0 to 1. So maybe we can even set up that initial integral. So from 0 to 1, I know I'm going to have a 2 pi outside. Now I just need to define r and h. So my h value, you can see, is going to be the vertical distance between my quadratic and my linear function. And we always do top minus bottom to make sure that that result is always positive. So h is going to be 2 minus x squared minus x. And then you can see that my radius, I'm going to zoom back in, is going to be the horizontal distance starting from the y, or from x equals 0 and moving towards the right. So that means that our radius is simply just x, because again, I need to define this radius in terms of x. So r is x. So you'll see that for these types of problems, if you're rotating it about one of your axes, it's your radius is either going to be x or y depending on the orientation of your rectangles. So we have 2 pi times r times h, 2 minus x squared minus x dx. And now the hard part is done. The rest is just evaluating our integral. So I'm going to distribute first. So 2 pi times x squared minus 1/4 x to the 4th minus 1/3 x cubed from 0 to 1. Sorry, this is supposed to be a 1. And here, so I have 2 pi times 1 minus 1/4 minus 1/3. So I get 5 pi over 6 units cubed. There you have it. All right, I have one for you to try on your own. So please pause the video and give it a shot. Hit play when you're ready to check. All right, go ahead and check your work here. So here's my original bounded region. So you can see that since I have a vertical axis of rotation, my cross section or the height is also vertical, and that means I'm going to have to slide them left to right. So I'm integrating with respect to x. And then you can see the height is the distance from my polynomial to the x-axis. So x minus x cubed minus 0. And my radius in terms of x, since again I'm starting at x equals 0, moving to the right, my radius is just x. So here's my integral, 2 pi r h from 0 to 1. And then you just simplify from there. All right, let's try another one together. So here we have y equals x squared and y equals 4x minus x squared. So this one actually has a vertex at 2, 4, and it's downward facing, and we know that this one has a vertex at the origin and upward facing. So my x squared ends up looking like this, and my other quadratic looks like this. So that's where they're going to intersect, so our bounded region is here, but you could continue your parabolas on if you want to. So my bounded region looks like this, and this time I'm rotating it about the line x equals 2. So again, I still have that vertical axis of rotation, which means that my cross section, which is my height, is also going to be vertical, and that means that I'm going to be integrating with respect to x, because I have to slide those from left to right to cover the entire surface or the entire area of my bounded region. Now let's see if we can define the height while we're at it. So I can see that the height is always going to be my second quadratic minus the first over that interval. So 4x minus x squared minus x squared. It's always top minus bottom, so the height is always positive. Now for this one, you can see that our radius, let's say I pick this arbitrary height. Again, it doesn't matter where this is in my area. That means that the radius would be this distance. So the distance from wherever my height is drawn to my axis of rotation. Now I need to define this in terms of x, because that's how I'm integrating. So I can use some other landmarks to kind of help me. I know that this distance from here to here is 2. And I know that this distance, just moving forward, is just x. If I'm starting at the origin, I'm moving to the right, that distance is just x. So I can see that r must be 2 minus x. So you can see as x increases, r is getting smaller and smaller. But when x is almost 0, r is almost the full length of 2. So we can define r as 2 minus x. So I think for these, that's usually the trickiest part. When your axis of rotation is no longer the x or y axis, you have to be careful when you're defining that radius. From there, the rest is the same. So we have 2 pi and then r and then h for x minus 2x squared dx, and then we're integrating from 0 to 2. Then the rest is just evaluating. So we'll do that real quick. We do need to multiply out your binomials. We have 2x cubed minus 8x squared plus 8x dx. And then we can find our antiderivative. And then from there, we're just plugging in numbers, really just plugging in 2. So 8 minus 64 thirds plus 16, which ends up being 16 pi over 3 units cubed. So again, just be really careful here when you're defining your radius, and everything for these problems so far has been in terms of x because that is how we're integrating. All right, go ahead and pause the video and give this one a try. And for this problem, you can just set up your integral and then use your calculator to evaluate it. All right, go ahead and check your work for this one. So here's my bounded region, and it's rotated about the line x equals 3. So you can see my cross section, my height is parallel to my axis rotation, and we can define that as the quadratic minus the x-axis. So here's our height. I am sliding that cross section left to right, so I'm integrating with respect to x, so that means that, again, my height and my radius need to be with respect to x. So for my radius, if I'm picking this arbitrary height, my radius is this distance, the distance from my axis of rotation to that height. So I know that I need to define it again in reference to x. So this distance is 3. If I'm starting at the origin and moving to the right, that distance is x. So I can see my radius is 3 minus x. Now, if I was on the left side of my y-axis, so if x is a negative value, think about it. It's going to be 3 minus a negative number, which actually gives you a larger radius, which is what would happen if you're moving farther to the left. So this way of describing your radius works for any radius within this interval. And we are integrating from -2 to 2. Then here's my integral. I skipped the work for this one, so if you did it by hand, it's 64 pi, or if you did it in your calculator, here's your decimal approximation. All right, let's try one last one together. So let's start with our bounded region. So x equals -y squared, and x equals -4. So I'm going to stop here because I see that I have that other bounded region, so here to here. Okay, now this one you can see that I'm rotating about the line y equals 4. So here's our first one where we actually have that horizontal axis of rotation. So here's my axis of rotation. So since my axis of rotation is horizontal, I know that that cross section that I use for my height needs to be parallel to that. So this is the first one where we have a horizontal cross section. So I'm going to define this as our height. And you can see that since I have a horizontal cross section, the only way to cover this entire area would be to stack them vertically. So for this one, I'm actually going to be integrating with respect to y. So that means that all of my equations also need to be with respect to y. This one is with respect to y already, so we don't need to rewrite it. We can define that height first. So we always want our height to be positive, so that means we need to do right minus left. So we would have -y squared minus -4. So right minus left. And that will be consistent over this entire interval. Now we need to define our radius. So if I zoom back in here, our radius is going to be this distance. So again, where I drew my height was totally arbitrary, but so my radius for that rectangle is going to be from the axis of rotation to that height. So remember, I need to define my radius in terms of y because I'm integrating with respect to y. So I know that, again, this entire distance here is 3. And then if I'm starting at the origin and I'm just moving up, that distance is always y. So if I want to define this radius, it's simply going to be 3 minus y. And remember, this also accounts for if you have a negative y value, because then it's 3 minus a negative number, and our radius is actually getting larger. So now I have all the information I need. So we say 2 pi, and then again we're integrating with respect to y, so from -2 to 2. And then we have r, and then h, -y squared plus 4 dy. So just be really careful that you know the orientation of your rectangles. You know what, if your axis of rotation is horizontal, that height cross section also must be horizontal. And then for this one, if you evaluate it all the way by hand, you would end up with 256 pi over 3, or you can plug it in your calculator to get a decimal approximation about this. But again, from there, the rest is just evaluating our definite integral, which I know you guys know how to do from last chapter. All right, I have one last one for you to try on your own. And for this problem, just set up the integral and then use your calculator to evaluate it. All right, go ahead and check your work here. So for this one, again, we have that horizontal axis of rotation. So I have my horizontal cross section, which I can define as 8 minus y cubed. So right minus left. And notice for this one, again, since my cross section is horizontal, I'm stacking them up to cover my area. So I'm integrating with respect to y. Here, my equation is already with respect to y, so I don't need to rewrite it. And then my radius, well, if I'm just going from y equals 0 in the positive direction, I can just define my radius as y. So here's 2 pi rh integrated from 0 to 2. All right, that's all for today's lesson. Thank you so much for watching.